Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments, and this is part one of an 11-part mini-series within that larger playlist. Now this mini-series deals with hierarchical designs, and we're going to deal with model development in this first example. So let me give you an example, and this is from Montgomery's book, that he talks about that a company receives raw material from 3 suppliers. And they want to test the purity of these samples. So what they do is for supplier 1, they randomly pick 3 batches to test, and then they do 4 different tests to see the purity on each of those. And for supplier 2, they randomly select 3 different batches from supplier 2, and then they test the purity, four times on within each batch. Supplier 3, they randomly pick 3 batches, and then they test the purity of each of those batches. Now, this is a nested design. It's what's called a 2-stage nested or hierarchical design. There's 2 factors. One is supplier and one is batch. Now, batch is considered nested within supplier, right? And the reason is there's no way to cross factors. Whenever you cross, it's the same level in one factor as it is in all the other levels of the other factor. But here, so batch 1 is not this same. It's not batch 1, right? It's different materials because it's within supplier 1. And so there's no way to cross these factors. Now, another way to think about it, we could just label them 1, 2, 3, 4, 5, 6, 7, 8, 9, and it's the same thing, right? There's 9 different batches here, so there's no way to cross, so it's hierarchical. Here, A is 3, B is 3, and N is 4. This is the number of reps. Now, the model that we'll choose, before I start, so let's say we wanted to test is batch 1 here equal to batch 2 here? And that really doesn't make sense because there could be a supplier effect. So really, to test within batches, it only makes sense to say, hey, is the purity of batch 1 equal to the purity of batch 2 within the same supplier? Otherwise, there's a supplier effect that's confounding. You can't separate that out. But what if we wanted to test, is supplier 1 the same as supplier 2, the purity of the samples? We could test that, right? And it's the average effect here is it equal to the average effect here? And that would test whether supplier 1 and supplier 2 are equal in the purity of their material. Now, the reason I'm pointing that out early on is because in, I think, part 4, we're going to talk about doing a test for supplier. But testing alpha 1 equal to alpha 2 is actually going to be the same as if we test if the average of these coefficients are the same as the average of these coefficients, right? That would be the exact same test. And in part 4, you'll go like, man, that's kind of confusing. But it makes sense here. So in the model would be Yijk. Is there some overall constant effect? Alpha I, so that's the supplier. There's a beta, but beta J, but that is, and this is an I in parentheses. It means that the factor for J, or factor B, is nested within factor I, or factor, this factor. The air terms are considered nested within the IJ combination. K is the number, the replicate within IJ. The airs are considered normal with a fixed constant. In matrix notation, we'll let that be Y is equal to X star beta star plus epsilon. So it's a linear model, but we're going to partition the X into something for the constant effect, the factor A, so alpha A or X alpha, and then the beta, for factor B, X beta. And so when you do this multiplication, you get this here. Mu times the one vector, alpha, x alpha times alpha, x beta times beta. Now, this is where it gets a little confusing, that there are, there can be A treatment effects. So there's A levels of factor A. So there's an alpha coefficient for each level. But within factor B, so it's nested within factor A, there's actually coefficients. There's B coefficients within level 1 of factor A. There's B coefficients in level 2 of factor A. So there's A times B beta coefficients. Oh, there it is. Yep. And so to me, it always helps to see the design matrix of this. And we're going to do this example where A is 3, B is 3, N is 4. So here, we have Y11, 1, Y112, Y113, Y114. And those are actually these here. So the way we're going to store it in matrix, we're going to go down this way, and down this way, down this way. And the reason is this coefficient, is all 1s here. And then over here, these are all 2, and these are all 3. So they change the slowest. Then we stay within batch. So these are all 1. These are all 2, the second index. The second index is 3. And then rep or response, it goes 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So that's the way we're putting them in here. All the way down to 3, 3, 4. So the beta coefficient is mu alpha 1, alpha 2, alpha 3. Then there's beta 1, 2, 3 within level 1 of factor A. 1, 2, 3 within factor 2. 1, 2, 3 within factor level 3 of factor A. Now these are all different. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different beta parameters. So when we do this multiplication, we're always going to pick off the mu. So there's a vector of all 1s. And then when we're within level 1 of factor A, we want to pick off the alpha. So it's all 1s. And then when we move to supplier 2, then we move over a column, and then those are all 1s for supplier 2. For supplier 3, we move over, and that's it. But now for the beta coefficients, this is a 1, 1, 1, 1. So we need a 1s there. We're going to pick off this coefficient for all 4 reps. And then the next one, we're going to pick off this coefficient for all 4 reps. And then the next, we're going to pick off this coefficient, and then we're going to go all the way down. So this is almost like diagonal, but it has a length of 1 all the way down. We hit each coefficient. Y is ABN by 1. X star, this design matrix, and wherever there's not a number, it's a 0. X star is ABN by 1 plus A plus AB, right? So there's 1, and then there's 3 columns here, so that's the A, and then there's A times B columns there, so that's what this represents. And the beta coefficient is 1 plus A plus AB by 1, so it's a vector. Yep. And this is X alpha, and this is X beta. And that's it. So that's model development for hierarchical designs. And hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.